Our next speaker is Itzhak Binderman from the School of Dentistry, actually from my department, from the Department of Oral Biology. So Itzhak is a dentist and also a scientist, and is a specialist in bone regeneration. And it's a great pleasure for me to introduce Itzhak, which is my personal mentor at the School of Dentistry.
Okay, thank you, Lihi, and thank you inviting me here to speak today. Although the subject is nano, but I think the scientific works are really macro. I will try to go with you through my lessons that I, during the years, learned from experiments on tissue engineering of bone. Well, it's classical that to produce a tissue, you need cells and you need a matrix. And although today we're using a lot of biomimetic materials and biomaterials and different materials, gels and so on, but I did most of my work I did essentially using normal cells, I'm talking about bone, and also normal matrix that the cells had in their memory. They knew those matrices in their memory. Now, what is the... Okay. First of all, let's see what is regeneration and what is tissue engineering. So regeneration essentially is the animal is creating back the exact structure of damaged cut tissue or organ automatically by its own biological power. No need for providing external scaffold or factors. This was known already and described by the Greeks almost 3,000 years ago. And you can see here the story of King Zeus, yes, that sent Heracles to slay the Lernan Hydra as the second of the set of labors. He was punished, Heracles, by Zeus. And he had just to cut and kill the Hydra. And you see in the vase this description showing you that he tries to cut the Hydra head, but what was the punishment? Because the Hydra head regenerated, and you had two heads. So regeneration was known already 3,000 years ago. Okay, nothing new. And only, in 81, this peptide or head activator peptide that brought to regeneration was very well established and isolated. And it's interesting to show you that now in 2019, it was published in Nature Communication in rats, the interaction between the Hydra head activator and the action on cellular activity. Now, tissue engineering. Tissue engineering, or it's called also regenerative medicine, has been defined as an interdisciplinary field that applies the principles of engineering and life sciences toward development of biological substitutes for the repair or regeneration of tissues and organs. As I mentioned before, the main factors here are stem cells and the matrix, the different matrices that are interacting, or the cells are using them as being activated by their attachment to the matrix, and then all other, of course, like strain and cytokines, growth factors, are essentially all together bringing to bone formation. But here's another point. This is also known, and this was described in the Genesis 1 in the Bible. We have two kinds of creation of men and women. One is Genesis 1. So God created man in his own image. In the image of God, he created him. Male and female, he created them, interestingly, maybe in the same person. Okay? Male. And then we have another description in Genesis 2. Here we have a typical, fantastic description of tissue engineering. Okay? So, here God caused a deep sleep to fall upon the man. And while he slept, so he did the surgery. You make a surgery with anesthesia. So the man will not feel essentially the surgery, right? And not only that you make the anesthesia, you also look if really the patient is sleeping, that he will not feel the surgery, right? So very well described. And now he took one of his ribs, rib is bone, a matrix, and in the rib we have also marrow cells, which are very important, and closed up with flesh, with cell, and another matrix. And the rib which the Lord God had from the man, he made into woman. Not created. Made is tissue engineering. It's not regeneration. Okay? So it's a fantastic description again of 3,000 years ago in the Bible. This is the first tissue engineering description. Okay, my story starts to find out how we can really culture cells. And this story goes back to when we published it in '74, when I spent time at the Weizmann Institute, and we were able to take embryonic, just embryos old, wow, he jumped all the lecture, sorry. No. Where are we? This is the end. Here I see. Okay, thank you. Yeah, fine. No, this will be 4. Thank you, that's it. Thank you. So here we described already in '74 a tissue culture of primary cells derived from old red calvaria, 1921 embryos, old, that we took the calvaria and periosteum, digested out the cells by trypsin EDTA, release the cells and grow them in culture. At that time we grew them in BJJ medium, which was a very essential medium to grow bone cells. And we have shown that the cells grow in multi-layers and that they calcify, yes, this is mineralization, on collagen fibers that they produce, type 1 fibers, and we were really published it and this culture we used essentially to understand how cells are activating and producing bone and also the matrix and also mineralize. Then further on we continued to study and we found that if we want to enrich the osteogenic cells from those primary calvaria and periosteum cells, which have also fibroblasts in them, yes, we used to culture them in low calcium in the medium. We found that low calcium medium, which means that in the medium we have no calcium, but only the calcium who came from the 10% fecal calf serum. And so we found that the low calcium, we had 2 populations, small cells and also large cells. And we knew also that this normal low calcium compared to normal is enriching the bone formation in the culture. So we separated by FACS the large and small cells and we cultured them, enriched them, And then we used a matrix which also we developed. What we did, we took from a rat femurs, and the femurs were cut, the epiphyses were cut, and only the diaphysis, the middle part, we essentially took out all the marrow and the trabecular bone. So we had a cylinder of diaphyseal bone. We demineralized it in 0.5 normal HCl of the diaphysis, and then put it in ethanol, 70% ethanol, until we used it. So we used this cylinder, demineralized bone cylinder, to put inside the small cells or the large cells and see if we can get in ectopic site in an animal, under the skin, subcutaneously, bone formation. As you can see here, we found that really this is the DBM cylinder, this is a histological section, and we found that new bone and osteoblasts are formed on the DBM, but most of the cylinder had connective, loose connective tissue with nice blood vessels, but the bone was only created on the wall of the DBM. Also in microradiography, we could see the bone was formed, nice bone was formed. This is essentially in the animal, under the skin. When we took large cells, we found that no bone was formed. So we had now, the small cells were really osteogenic cells, which produced bone in this ectopic model, while large cells were essentially producing only some connective tissue. So we said that the direct interaction of osteogenic progenitors with the DBM scaffold stimulated the position of bone on the DBM surfaces. Okay? So not the whole volume was essentially formed by the bone. This is essentially typical to what today most of the people use. They use a stem cell or a progenitor cell. They use a matrix. They grow the cells on the matrix, and then they put it in a bone defect. Okay. There's another model which we worked on, and this model was taking fresh marrow cells, not stem cells, not taking progenitor cells, but taking fresh marrow, implant in the same way into DBM cylinder, and put it ectopically in a rat. And here, after 3 to 4 weeks, we found that bone formation was present, as you can see here. After 4 weeks, this is the DBM cylinder, and all the space was filled with new bone, and even new marrow was formed. Now, if we didn't use bone marrow in the cylinder, we had no bone formation. So the marrow, fresh marrow, had all the ability to produce this bone, and the bone was filling the whole space. Now, what is bone marrow? So bone marrow is, of course, has hematopoietic stem cells and has also mesenchymal stem cells. But we have to understand that the number of hematopoietic stem cells is much higher than the mesenchymal stem cells. On one mesenchymal cells is in 100,000 hematopoietic cells. So this is essentially the ratio. But anyhow, we have here two kinds of interactions. One interaction is that on the left side we see that mesenchymal stem cells can of course develop into osteoblasts and osteocytes and produce bone. On the other hand, we have another pathway that monocytes or macrophages can also interact with the mesenchymal cells and can produce osteoblasts and then osteocytes. Here we have the biomaterial. And let's consider what are the cells that when we put a biomaterial inside, or into a wound even, what are the cells, the first cells that touching this biomaterial? Mostly those are macrophages. They are not stem cells. They are not progenitor cells. They are not mesenchymal cells, because this is the majority what we have in the wound. So we have to consider that the most important part is, as it was described here, that the monocytes or the resident macrophages, yes, are essentially important, because the macrophage at the first stage of the inflammatory process is M1, which is important in the inflammatory process, but then he has to switch into M2 in order to make a repair, in order to activate the stem cells to produce, in this case, a bone. So these are the two mechanisms, one which was described on the left side, essentially progenitor cells with the matrix, and on the right cell, on the right here, is the marrow intervention also of macrophages from the marrow that essentially sensed the matrix and activated mesenchymal cells. Now, also what we know, for example, here we can show that after 3 days, if we look at the marrow in the DBM, this is very interesting, it's almost going to die, a lot of cell death. However, if you look for the phenotypic expression of this marrow compared to day 0, we have the osteogenic phenotype expressed very much, even at 3 days after implantation of the marrow into the DBM. After 7 days, we can see that on the DBM, we can see here cartilage, okay? And here we can ingrowth of bone from the orifice of the marrow, of the DBM. And this is after 14, 21 days. And here we can see essentially by microradiography how it's growing. After 2 weeks, we can see from the two openings of the DBM, bone is formed. And then after 3 weeks and after 4 weeks. So this is essentially a very nice model that we can use also to study if we put here any kind of material and we want to know if this is disturbing bone formation or is activating more bone formation. This can be studied, and we did it also in our studies to show. So here I would say that the bone marrow cell population induce endochondral bones starting from DBM openings and fill the whole volume of DBM cylinder, almost regenerating the ossicule. Very different from osteoprogenitor and DBM. So let's see and maybe look into what happens, what is the pathway of wound healing during tissue engineering surgery. So after we can see here the table, what happens in wound healing about ECM, how it's changing, and the cells, how they change. And what we see here, that this is the wound here, okay, and what is in this wound is described here, which is essentially fibrin, fibronectin, and other molecules from the blood. This is not marrow, this is blood. But we have also cells, the majority of them are monocytes, which become macrophages. So the macrophages and the monocytes are very important in repair of any tissue and also of bone tissue. And this is when we put it here, any kind of biomaterial. This is what is the interaction, which is here, depends very much how much the macrophages are sensing the biomaterial. If the biomaterial is very biocompatible, then the macrophages will go from M1 to M2, and we shall have a nice repair or regeneration of the tissue. While if we are stopped in M1 phenotype of macrophages, we shall have granulation tissue and pathology. So essentially, again, today, if we want to learn and study tissue engineering, we have to take into account the most important cell is the macrophages. And now at the end, I will just show you that if we take marrow, not from young animals, but from sedentary and obese animals, okay, and we put this bone marrow in the DBM cylinder, as I showed you before, we don't get bone. Or sometimes we get a little bit of bone. But so what we did exercise those animals, those obese old animals, as you can see. Sorry, this is a wheel. Oh. This is a wheel here, a running wheel of the animals, and they run much less than the young, by the way, but this was enough for them that after 2 weeks of exercising the old obese animals, what we find that new bone was formed compared to the sedentary. Okay? And we now know also that the marrow of those obese animals is changing from fatty marrow into hematopoietic marrow, which creates a lot of probably monocytes. So I would conclude that, and this was another paper which is very interesting to read, that running or exercising, not running, but going 45 minutes, you can change your wound healing for much better wound healing and repair by switching the M1 macrophages to M2, while here in adipose tissue, the M2 are switched back to M1, and the dominant cell is the M1. So, summarizing it, we have to add to the first diagram here another very important factor, macrophages, that are very important because those are the first cells, they essentially sense the matrix that we're using to test it. Thank you very much.
Thank you. So any questions? Okay, so I would like to ask, so how do you think this change from M1 to M2 can affect the DBM structures or any scaffold?
Well, they are today, because we know now that, for example, the M1, yes, is producing a lot of cytokines. And those cytokines essentially are inflammatory. They are called inflammatory cells. While the M2 is the anti-inflammatory cells, or the repair macrophages. And they, when you switch from M1 to M2, there are a few ways with, one is, I believe, interleukin 10, and so on, that you activate the M2, and the M2 starts to produce VEGF, which brings the blood, like we saw, into the DBM cylinder, and with the blood, around the blood, you have also the pericytes, which are the stem cells or progenitors, which can form a new tissue. So I think that before we going to use progenitors or stem cells with a biomaterial to see and test it whether it's biocompatible, I think we should go and test with the sensor cells, which are the macrophages, and see. And then we can probably maybe define and produce biomaterials which will switch fast from M1 to M2.
Okay, so I would like to thank Itzhak and all the speakers of this session.